Hi, thanks for joining me. Today I'm going to be going over something which may or may not be a coincidence in maths. If we take 1 cubed plus 5 cubed plus 3 cubed, we get 153. If we do 16 cubed plus 50 cubed plus 33 cubed, we get 165,033. So 16, 50, 33. And if we do 166 cubed plus 500 cubed plus 333 cubed, we get 166,500,333. Now, is this a coincidence? Or is there some interesting pattern going on behind the scenes? Let's dive right in. Okay, so we're going to start by calling xn to be 1 followed by n minus 1 sixes. So an n-digit number where the first digit is 1 and the rest are sixes. Yn is going to be 5 followed by n minus 1 zeros. And Zn is just the n-digit number with all threes. And essentially what we're trying to explore is it the case that xn cubed plus yn cubed plus zn cubed is kind of xn written next to yn written next to zn, if we think about that as a 3n digit number. The fancy way of sort of what we call that process of sticking numbers next to each other is called concatenating. So I'm going to use this kind of star to denote concatenation. So we want to know, is it the case that xn cubed plus yn cubed plus zn cubed equals xn concatenated with yn concatenated with zn for all n? And just to be super clear with what I mean by concatenation, if I was doing 20 concatenated with 23, I would get 2023. So just writing the numbers next to each other. And again, of course, throughout this problem, we're going to be working base 10. So there's no ambiguity by what I mean here. Anyway, let's go back to the problem. How on earth can we go about trying to start from this thing and prove that it's this concatenation? Well, the best way to start is trying to understand how we can use this concatenation. And the way we do that is by thinking about this number 20 concatenated with 23 as not 20 concatenated with 23, but it's 2023, which I could write as 20 times 100 plus 23 times 1. Now, what I mean by that is, what I'm going to do is look at these xn, yns, and zns as sums of, or linear sums of powers of 10. So, for example, xn. What is xn? Well, it's 1 followed by a bunch of 6s. And it's an n-digit number in total. So this 1 here tells me that this is going to be 1 times 10 to the power of n minus 1. And then this 6 here is going to be 6 times 10 to the power of n minus 2. And then this 6 here will be plus 6 times 10 to the n minus 3. And so on, all the way down to 6 times 10 to the 0. So, for example, if we had 3 digits here, so if we're looking at x3, that would be 166. So this is when n equals 3, so we get 1 times 10 squared, that gives us the 100. N is 3, so 3 minus 2 is 1, so 6 times 10 to the 1, so 6 times 10 is the 60. And then finally, n minus 3 would be 0, so we get 6 times 10 to the 0, so 6 times 1, which is the 6 there. So we're essentially writing 166 as 1 times 100 plus 6 times 10 plus 6 times 1. But of course, that's the case where n is 3, so we're just going to do this more generally for any n. And we write it like this. Okay, well this 1 times 10 to the n minus 1, this is just going to still be 10 to the n minus 1. But now what I notice here is this is a geometric progression. I've got, if I take out the factor of 6, I'm just adding up powers of 10, starting from 1, ending up at 10 to the n minus 2, and there's a nice formula for this. It's going to be 10 to the n minus 1 minus 1, all divided by 10 minus 1. And now, of course, I can simplify this. 10 minus 1 on the bottom is 9, 6 over 9 is 2/3, so I can write this as 10 to the n minus 1, this guy here, plus 2/3 times 10 to the n minus 1, minus 2/3. So 6 over 9 times 10 to the n minus 1 is 2/3, and then minus 1 times 2/3 is a minus 2/3. And finally, this is just 5/3 times 10 to the n minus 1, minus 2/3. Okay, so now I've written xn in a slightly, well, in a different form. 5/3 10 to the n minus 1 minus 2/3. What I'm going to do is do something similar for yn and zn, bring them all together and see how we can work with this thing here and somehow arrive at this thing here. Okay, so you can also show that yn is a half times 10 to the n, and zn is a third times 10 to the n minus 1. And in fact, this expression for xn that we derived, I'm going to write slightly differently. You can actually show that this is just a sixth times 10 to the n minus 4. So taking out a factor of 6, and you get 10 to the n minus 4. And now you can see that everything has a 10 to the n in it. Okay, so let's look at xn and let's cube it. And to do this, we're just going to use the binomial theorem. So we've got 1 over 6 cubed, and then we want to do 10 to the n minus 4 cubed. So as I say, we can just use the binomial theorem. This is going to be, we'll keep the 1 over 6 cubed out here. 10 over n cubed is 10 to the 3n. Then we've got to subtract off a 3 choose 1, which is 3 times 4 times 10 to the 2n. Then we've got to add 3 choose 2, which is 3 times 4 squared times 10 to the n, and then finally subtract off 4 cubed, which is 64. And if you go through the details and just simplify this, you're going to get 1 over 216 times 10 to the 3n. Then you're going to subtract 1 over 18 times 10 to the 2n, add 2/9 of 10 to the n, and minus 8 over 27. So of course I've done this separately. Now this is 10 to the something times 10 to the 3n plus something times 10 to the 2n plus something times 10 to the n, and then a constant. And we're going to get something similar when we look at yn cubed, or in fact we can straight away see what yn cubed is going to be. It's just going to be 1 over 8 times 10 to the 3n. And you can do something similar with zn. If you expand out what zn cubed is and simplify, you get zn cubed is equal to 1 over 27 times 10 to the 3n minus 1 over 9 times 10 to the 2n plus 1 over 9 times 10 to the n minus 1 over 27. So now we have expressions for xn cubed, yn cubed, and zn cubed as linear combinations of powers of 10. So what we can do now is add them up, simplify, and have an expression for xn cubed plus yn cubed plus zn cubed as linear sums of powers of 10. Okay, so I've saved you the algebra of having to work out what xn cubed plus yn cubed plus zn cubed is. I've simplified it and we get this expression here, a sixth times 10 to the 3n minus a sixth times 10 to the 2n plus a third times 10 to the n minus a third. Now you might think what we have to do next is consider the number, well, xn concatenated with yn concatenated with zn, and then write this as the sums of powers of 10. And now we could do that, but there's actually a nice little trick. We notice just by staring at this, we've got a sixth times 10 to the 3n minus a sixth times 10 to the 2n. So it looks quite similar. And similarly, we've got a third times 10 to the n minus a third. So we've got a lot of repetition or similar numbers in our expression. And so let's focus on this bit first. So it's a sixth times 10 to the 3n. So we're taking 10 to the 3n, so that's 1 followed by 3n0. So 10 to the 3n is a 3n plus 1 digit number, and then we're dividing by 6. So it's going to be a 3n digit number with 0.6 recurring after the decimal point. So it's actually going to be 1, 6, 6, 6, and so on, 6, and that's going to be 3n digits, 0.666. So if I call this the first bit alpha, or alpha n, so this thing here is alpha n, well, the first bit of it. So 1 followed by 3n minus 1 sixes, 0.66666 recurring. Okay, and now how about this thing here, a sixth times 10 to the 2n? Well, it's a similar sort of thing. We've got 10 to the 2n, which is 1 followed by 2n zeros. So 10 to the 2n is a 2n plus 1 digit number. Then we're dividing by 6, so it's going to become a 2n digit number, and it's going to be 16666.6 recurring as well. So 16666, so on 6. So there's 2n digits there in total, 0.6 recurring after the decimal point. And of course we're doing this minus this, so what's quite nice is the bits after the decimal cancel out with one another. And so we've got a 3n digit number minus a 2n digit number. So we can see that the first n digits of this number are going to be unchanged. So it's going to be 1, 6, 6, and so on 6. So that bit's going to be the n digit number. And now perhaps you can see things starting to fall together. And now what are we left with? Well, we're left with 6, 6, 6, 6, 6, 2n lots of 6's minus this. So the final 2n minus 1 6's will cancel out. So we've got 6, 6, 6, so 2n of those, from here, minus 166666. And if we do this, this 6 will cancel with that 6, this 6 will cancel with that 6, and so on. But we have 6 minus 1 at the front, so that's going to be 5, followed by a bunch of zeros. So it's going to be 5, 0, 0, 0, 0. And that there is an n-digit number. So this first thing here is going to be, well, I say an n-digit number, it's actually going to be a 2n-digit number because we've got 2n here. So it's going to be a 3n digit number in total. So the first n digits is 1 followed by n minus 1 sixes, and then we've got 5 followed by 2n minus 1 zeros. Now we've still got this bit at the end here, a third times 10 to the n minus a third. Now what is a third of 10 to the n? Well, 10 to the n is 1 followed by n zeros. So when we divide it by 3, it's going to be an n digit number. It's going to be 3, 3, 3, 3, 3, and so on, 0.3 recurring. So then if we subtract off the third, we're going to be subtracting off 3, 3, and so on, all the way up to 3. Like so. Oh, sorry, not subtracting, adding. I don't know why I said subtract. How many 3's have we got? We've got n of them. And if we add it onto this number here, you can see the last n digits of this number here are all 0. So when we add this 3 here, we're finally going to get the number we're expecting. So there's n digits there, 5, followed by a bunch of zeros, n there, and then 3, bunch of 3's, and there are n digits there. So it turns out that this is not a coincidence, and in fact xn cubed plus yn cubed plus zn cubed always equals this bizarre number here. Now, I guess a question to ask yourself is, why is this? So it's not a coincidence. We've proved that it's always going to be true for all values of n. But why? Why is it true? What is the underlying math here? We've kind of just proved it algebraically. But why is it true? And if it is the case that we can work out why it is true, can we construct other examples? So leave your thoughts in the comments down below. I'll be intrigued to see what you guys have got to say about this problem. I thought this was quite cool, and when I first saw it, I thought, no, this surely has to be a coincidence. But then you chug through the algebra, and it turns out that it's not a coincidence, and I think that it's super beautiful. Anyway, I will stop waffling now. Thank you very much for watching. If you have enjoyed this video, please do give it a like, and if you are new to the channel, please do consider subscribing as well. Thank you very much for your time. I will catch you in the next one. Have a great day.